Blockchain technology has evolved significantly since the introduction of Bitcoin in 2009. The foundational premise of blockchain is the use of a decentralized ledger that enables multiple participants to reach a consensus on the outcome of events, such as transactions, without the need to rely on centralized intermediaries. To ensure participants agree on the state of the network, blockchains use a consensus mechanism. Consensus mechanisms are processes followed to achieve agreement across a decentralized network while maintaining trust and security. Bitcoin utilizes a proof-of-work consensus mechanism, which relies on computational power to reach consensus, validate transactions, and secure the network. As the blockchain industry has matured, new types of consensus mechanisms emerged. The most popular consensus mechanism in recent years is proof of stake, which relies on a process called staking. The concept of proof of stake was first introduced in 2011 by Sonny King and Scott Nadal in their Peercoin white paper. It emerged as an alternative to the energy-intensive proof-of-work model, which requires miners to solve complex cryptographic problems to validate transactions and secure the network. To solve these complex problems, proof-of-work miners need to use massive computational power. Over time, many industry participants argue that the capital expenditure and operational costs of mining Bitcoin have become a barrier for smaller players, leading to the centralization of mining pools. Additionally, proof-of-work as a consensus mechanism also has a challenge in scaling up its transaction throughput. As a result, the majority of newer blockchain networks have decided to adopt a different consensus mechanism than proof-of-work, with proof-of-stake being one of the most popular alternatives.
In proof-of-stake networks, miners are commonly called validators. Validators are responsible for the same actions that miners do in proof-of-work networks, such as validating transactions and securing the network. However, instead of deploying computational power, validators are required to stake the native token associated with the underlying blockchain network that they are participating in.
There are numerous implementations of proof-of-stake. At its core, proof-of-stake validators are chosen to create new blocks and validate transactions based on the number of tokens they hold and are willing to stake as collateral. Validators are then incentivized to do the right thing, as their staked tokens can be forfeited if they act maliciously or harm the network. Instead of risking capital in the form of mining rigs and operational costs, as they would in a proof-of-work blockchain, validators in a proof-of-stake network risk their capital in the form of the native tokens associated with the underlying blockchain. In proof-of-work, miners risk USD-denominated capital through operational, electrical, and hardware costs, which does not incentivize miners to keep their mining rewards. Proof-of-work miners often sell their rewards to cover expenses or to purchase more mining rigs to scale up their operations and capture market share. In proof-of-stake, validators stake the native token of the blockchain they are validating instead of purchasing mining rigs. As a result, validators are not risking USD-denominated assets. This aligns incentives between the validators and the blockchain network while reducing the need to sell their reward to cover expenses. The goal is to create a compounding loop that increases their market share and consequently their rewards if validators decide to stake their rewards. Proponents of proof-of-stake argue that this compounding loop contributes to the safety of the consensus mechanism, as validators have a vested interest in the long-term health of the network due to their staked tokens. This makes it expensive and unprofitable for attackers to compromise the network. On the other side, those against proof-of-stake argue that implementation of proof-of-stake often adds a layer of centralization. For instance, delegated proof-of-stake is a version of proof-of-stake whereby stakers select delegates to validate the network, outsourcing the required work to a third party for a small fee taken from earned staking rewards. There are two additional benefits of proof-of-stake related to yield and energy efficiency. The rewards generated from proof-of-stake networks are a substantial source of yield. Yield generated from staking and participating in a blockchain network is equivalent to a stock dividend that is automatically reinvested in the underlying equity. By contrast, in proof-of-work systems, there is no pathway for an asset owner to receive more of the same asset by participating in the network. Proof-of-work assets, such as Bitcoin, require asset owners to lend out the asset in order to receive yield. Proof-of-work requires computational power for miners to effectively do their job. At a large enough scale, the energy consumed can be extremely significant. As the second largest digital asset by market capitalization, Ethereum was using 5.13 gigawatts on a continuing basis with proof of work, or roughly equivalent to the same amount of energy consumed by 2,100 American homes. After transitioning to proof of stake, Ethereum is using 30,000 times less energy. Today, many of the top digital assets by market capitalization are using proof of stake consensus mechanisms. Ethereum, which has more than $27 billion in total value locked across its DeFi ecosystem, transitioned to proof of stake in September 2022. Additionally, 11 out of the top 25 digital assets by market capitalization are using proof of stake. Proof of stake and staking activities are significant components of the digital asset market. The majority of top assets by market capitalization with smart contract functionality have adopted proof of stake in recent years. While there are ongoing discussions and improvements that can be implemented in the existing proof of stake landscape, proof of stake is currently the dominant consensus mechanism for Web3 and decentralized applications.